sound, he cannot hear us.
We will start in a few minutes.
Oh, yes, I suggest we start quite rapidly. It's 3:30 p.m.
Yeah,
so
we can wait 1 minute or two.
Okay, we can do that. Who's missing? Nicola is missing.
Okay, I guess we can start.
Yes,
Welcome
now I can hear.
hello. Welcome, everyone. This is the Coding for Efficient Network Communication Research Group. Next slide.
Sorry.
Oh, and well, I'm Marie-Josée Montpetit, and my co-chair Vincent is there too. So our goals, which have not changed since a long time, is to foster research in network and application layer coding, and the goal is to improve network performance. So through the years, we looked at coding libraries, the protocols to use these codes, and a lot of real-world use cases. And there's work in progress, especially in congestion control, for example. Next slide. So IPR has always been a problem with this group. We remind everybody that everything that is presented here, if you have IPR, should be disclosed, and that the group should be aware of it. Next slide. There's also a code of conduct. There were issues this week in the IETF about people who had not read that and instead of bullying people, and that's not acceptable. So next slide. So the goal of the IETF, I think it's also extremely important, and this is not a warning, but an advice to everyone presenting. We are not standardization. We're not there to standardize anything. We're there to foster research, to present research, to essentially create research communities around network coding, and not just to present a bunch of solutions for standardization, which is not the role. So please, when you present, highlight what is the role of the research and what the community will gain from it. Next slide. So great that we're online. It's recorded, so we can do the minutes later. We didn't have anyone to take minutes, but I guess we can do it from the recording. It's great also that the blue sheet is now automatically generated, so don't worry. We know you're there. Well, we know you're there. Big Brother's watching you, I guess. And you can actually press the raise hand if you want to talk and if you want to ask questions. I would say also another great way of asking questions is putting question in the chat, and both Vincent and I will monitor the chat to make sure that we know that you're in line for a question. Next slide. So our agenda, there's me now. Hopefully it won't be 10 minutes. And then we're going to have the presentation on BATS, which is a coding scheme for multi-hop. Obviously, the ongoing research on coding and congestion control, which is also done in almost collaboration with our friends in the congestion control research group, and more from Morten about latency and reliability for block and sliding codes. And then we wrap up. So we have a new RFC since last time. Congratulations to every author. We have the one that I should be more forceful on, but I've been busy on other things, but we actually are pushing the NC for CC and ICN. We have BATS that's kind of ready to move on to becoming more than an RG document, but also going to last call. And the coding for congestion control is also very much progressing, and there's going to be presentations on those two drafts today. So the action needed is the coding for Quick. We have decided to put it on hold a little bit while Quick was deciding what they were going to do. And we have to decide if we want to push that to be a quick draft or what we want to do with it. And then there's Tetris. The group of Tetris has actually told us that they wanted to continue the document and put it to a level where it could be pushed forward also to the IESG. Next slide. So maybe our plan is to meet at IETF 111. We will meet probably at an interim to make sure we do that. We want to close the group. I think we've achieved everything we wanted to do. And since there's the research community is not as large as it was, and I think in terms of our milestone, we met everything. So we plan to close the group at IETF 111. That's it?
Yeah, that's it. Well done. Thank you. So now the next presentation is from Raymond. So Raymond, can you come up? I have your slides.
Yes, I'm here. Yeah.
Yeah, I will share your slides now. Yes, that's the right button. It's arriving. Yep. Here we are.
Okay.
I will switch off my video. If you can put your own video, that's
okay,
nice.
Yeah.
If you want, up to you.
Yeah, sure. Yeah. Hello, everybody. Good morning. Good afternoon. It's nighttime in Hong Kong. So I'm going to give you an update on the deployment of BATS codes. Next slide, please. Okay, so just a few very quick brief introduction. Why do we care about BATS? Because in wireless communication, multi-hop is a long-standing problem. If data packets are treated as commodities, when you go through different hops, then the packet loss will keep accumulating, and that's why usually after a few hops, it's very hard to transmit, for example, in particular, video very smoothly. And in the industry, sometimes this is referred to as the multi-hop curse. And by doing recoding at the intermediate nodes, BATS, which is an efficient implementation of network coding, the transmission can sustain tens or even hundreds of hops without relying on link-by-link retransmission, which, by the way, is very bad for video transmission, as many of us know. Next slide, please. Okay, here's a monograph that I published with Shenghao Yang back in 2017. Next slide, please. Okay, here's a quick performance comparison. Assuming that there's a 20% packet loss on each link, then the red curve is the performance, the throughput for any routing-based protocol. Could be TCP/IP or end-to-end fountain code. x-axis is the number of hops, and the y-axis is the throughput. And we can see that when the number of hops increases, then the throughput actually decreases exponentially fast, because every time you multiply by 0.8. And whereas for batch code, the throughput can sustain very well, and after 50 hops, the throughput can still sustain at about 0.7. Next slide, please. And even after 1,000 hops, the throughput can still be around 0.66. Next one, please. Okay, our first employment of batch code is actually in the Hong Kong government's Smart Lamppost project. Next, please. Okay, so this is an illustration of the system. Suppose on the same street, we have a number of lampposts, and the left one is connected to an optical fiber, and the rest are connected through this wireless multi-hop network enabled by batch code. Next, please. Okay, so in 2019, we successfully deployed bats in 36 smart lampposts. However, due to the social unrest, the general public has concern about the installation of video cameras on the lamppost due to possible infringement of privacy. And however, we learned that it is quite hopeful that the project can resume by the end of this year with the video cameras replaced by LiDARs. Next one, please. Okay, there's a picture of the smart lamppost that we have deployed. Next, please. Okay, currently we are building a smart lamppost testbed on CHK, that's my university, the Chinese University of Hong Kong campus. Next, please. Okay, so what we are, well, one thing I would like to bring up is something quite interesting, because BATS is inherently a fog computing application, because the computation must be done at the edge. Okay, there's no choice. And so we're going to install 20 fog computing based smart lampposts on our campus, with BATS being provided as a service. And after the network is being set up, different services will be provided, including Wi-Fi access, lamppost assisted autonomous driving, real-time traffic monitoring with AI application. Next, please. Okay, this is a picture of the smart lampposts we are building on campus. As you can see, they're not as fancy as the one we just saw a moment ago. Next, please. Okay, we also have started a new pilot trial at one of the country parks in Hong Kong. Next, please. So in this picture, in this map, you see that we're going to build a 4-node pilot trial in a country park, which is not well covered by the cellular network, and that poses threats to hikers, in addition to being inconvenient. Okay, so what we're going to do is to extend the network to the country park via the BATS technology. Next, please. Okay, so this is a picture of one of the nodes, which is driven by solar power, because there's no power available, or no electric power available over there. And beneath the solar panel are the equipments, and you see that on the pole. And the poles, there are some. These are the antennas. Okay. Next, please. So during the past few years, we have been exploring different opportunities, and we have identified quite a number of potential applications of BATS. So these include satellite communications, rural communications, okay, private networks, rapid response network, smart cities like smart lampposts and things like that, V2X, safety and surveillance, Internet of Things, confined space like mining tunnels, 5G access networks, power line communications, and also underwater acoustic communications. Next, please. Okay, currently we are building an FPGA to implement the best coding algorithm. And for this project, we are working with Intel and Aero Electronics. Okay, next, please. Okay, so we have submitted an internet draft, as many of us know, and the latest update is on February 2nd this year. Next, please. So this draft consists of a couple of sections. We have one section on the basic data delivery procedures using a BATS code. We have one section on a baseline BATS code specification. And there's a new section on related research issues, including coding design issues, protocol design issues, and applications related issues. And we also have a section discussing the security issues related to BATS. Next, please. So I would like to take this opportunity to thank the two chairs, Maria Jose and Vincent, and for the suggestion to add discussions on related research issues, and also to Dave Oran for the pointer to the recent work by Byers and Luby on the so-called liquid data networking. So indeed, BATS is a suitable candidate for the erasure correction code in liquid data networking in the presence of multiple hops in the network. Okay, next, please. So this is a list of the IPs that we have filed so far, and most of them have already been granted, except for one or two which are pending. And next, please. Okay, so actually this is the PDF file in the PowerPoint file. There's actually a very interesting animation to entertain you. You see cars running around. And so this is the end of my talk. Thank you. Is there any questions?
Okay, sorry, I was muted. Thank you very much, Raymond, for your presentation. Is there any question from the audience? I haven't seen any so far. Otherwise, I have. Okay. Yes, there's somebody.
Watson Lad Cloudflare. This is really interesting work. Is there, if this research group disbands sort of 6 months or 3 months from now, how are we going to advance the draft?
How are we going to expand the draft?
It's the draft, as in move it closer to publication. This is really cool.
I think it is pretty ready for publication.
Yes, I can add something. I've been through this brand new section 4 about research issues. I found it, generally speaking, very well written and very clear. We have many references to key research topics, so that's very great. And I've also been through the security considerations new section, and that's well, I have a few comments on for each of them, but generally speaking, they are pretty nice sections. I haven't read so far the specification once again, so I will do that. But I have the feeling that except a few minor modifications, we are very close to the end with this document. So I'm very happy with this, the way it moved forward, and especially this the addition of this new research section. That's great. That's great. If I can, I would just do a general comment for this section 4. So it's very well written. No problem for that. Very synthetic manner, so that's great. I may just have one comment. It can be understood as some advertisement for that. So I understand that it's in some way unavoidable. That's not the problem. But if you can, I would say, make it a bit more generic, it would be great, I think. A bit more neutral, I would say.
Okay. So
I don't think it's a big deal. It's no problem if there are many references to that, but if you can make it more generic anyway, that would be great. That's
you
just
mean
the.
We will reduce the number of references, or?
Yeah, it can be. Yeah, that can be a way to do that. Yeah.
Oh, okay.
I don't know what
we'll
the others think about it, but that's what I would say, as far as I'm concerned.
Okay. Thank you.
Yes, I see, Dave. Do you want to speak? The floor is yours.
Hi, I'm not trying to speak for Colin here, but just reflecting on Watson's comment. What we've done, I believe, in the IETF in the past is we put a working research group to sleep while there's still documents going through the process, and don't formally close it till the last one's been disposed of. So I think what'll probably happen is if we're done, the active need to meet and exchange stuff, we'll just put the research group to sleep until everything gets through the process.
Yeah, thank you. Other opinion, other comments for this document? Nobody? Are we done? Okay, it seems.
Well, thank you very much.
Yeah.
Okay, thank you very much.
Thank you so much. Yes, and I'm quite confident that we can have it start a working group, a research group last call quite soon for this document. It shouldn't be a big deal. So thank you so much for your efforts and the quality of the doc. So now it's time to switch to the next session. I will upload the slides, share the slides, sorry. Nicolas?
Can you hear me?
Yes, we can hear you.
Perfect. Hello, everyone. So I'm presenting the draft update on the draft on congestion. This is the 6th version of the document. So there are some things that I've presented in previous IETF meetings. I have letted them in this deck in case there were some persons that were not there at that moment.
Sorry, Nicolas. The quality, the audio quality is quite bad. There is some echo. I will switch off my mic.
Is it better now? Is it better? I'm trying. Okay. Not really.
It is better.
Thank you.
It is better.
So it slides. There are too much content to what is actually new. But I wanted to make on the previous version of the document what is now in the document. This is.
There is an incredible echo. There is an incredible echo. Somebody probably has. Can everybody put themselves a loop? So can everybody put themselves on mute?
Just me or? Otherwise. Okay, I will take this as a yes. I just have some issues to follow the screen. So basically, we had some comments on live the previous meeting, and this helped us to improve the document. So I will try to make an emphasis on that during the presentation. So next slide, please. So next is something that was already that we presented before. Not describe it further. This set of experiments we have run over different set characteristics. So I think the main point that we want to highlight is on the slide. we have a lossy satellite, and we use either TCP or congestion controls. So can you go next slide, please?
Nicolas, it's very difficult to understand you. So maybe okay. So there is a suggestion in the list. Find the chat that you what's it saying?
Can you hear?
Yes. So try to connect again. Oh, please speak.
Can you hear me now?
It's much better now.
Okay, perfect. Sorry for that. So can you hit 4, please? In case it work really well, I will just not want to focus at a slide already presented. Next slide.
The sound came back to be terrible.
Is it better?
Go on, speak.
Okay.
We cannot see.
So on slide 4, we just show that having FEC improved a lot with the download and the downloading time of 20 megabytes. But then what is interesting is that the results are very different from TCP and QUIC. So that the main point we wanted to make is that FEC doesn't have the same impact on all the congestion controls. Then if we go to slide 6, what is shown at IETF 109 is that when we have, I want to focus on the graph at the bottom, is that basically when we have coded TCP flows, they just take the whole capacity. So there can be lots of fairness issues when you use coding without considering congestion control. So the objective of the slides is shown on slide 7. Basically, when we use coding, we can help dealing with losses at the end of transfers, or when we have networks with non-congestion losses, but we should not hide congestion signals. So the objective of the draft is to describe how FEC and congestion control can coexist. And as soon as we have some research on, let's put coding in a congestion control, we should consider the aspects that are discussed in this draft. If we go to slide 8, this basically shows the main changes as the last IETF. Basically, we have realized the whole document. How of the figure is not to go now into the details on, but just to show that there were lots of changes. Basically, IETF 109, we had comments on adding artist transport multipass, discussions on reliability and partial on partial. So we have some things aspect in the current version. And also, thank you, Vincent, very much for first review the document on the list. So we have tried to include most of them in the dated version, and other issues that were more complicated to assess quickly have been added as issues and are here on these slides to be discussed today. So what discussed, if you go to next slide, is also something that we have added in the document is what is fairness. So there is this paper that was presented in .NET in 19 on what is fairness, and I think that is we are defining it in the draft. It's just saying that we measure fairness as the impact of coding flows when they share a bottleneck. Next slide, please. It's just some comments on what is and what is not in the scope of this document. I think this was not clear. Vincent asked something to clarify this, so we have may include. So the picture that is here will be in the next version of the document. It's not in the current one that has been published for the IETF. But basically, what we want to say that an application may be composed of several streams, and we do not consider the impact of multi-streams and how they interact each other. That being said, we may have a FEC. It is above a multipath transpath composed of different subflows, and we may have also FEC below a multipath transport, but in this case applies to the single flows, not to combination of the flows. Next slide, please, is just recalling what we have in this document. Basically, we have if you have FEC that is above, in or below congestion control. So we discuss these different cases in the and in version in the previous version we discussed with fairness, how you deal with recovered symbols, how you adapt coding rates, and what you use less per symbol. In the current version, we have added discussions on partial ordering, partial reliability, and multipath transport. So the slide was presented previously, and so I will not go into the details. The one, so 13. Next slide, please. Is what is new in this version of the document. So I don't have time. I have to go into the details we have here. I think it's very wordy, and it was more for everyone to know through the mailing list. If you have any comments on different boxes, we tried to cover all the cases, and we hope there is what we have done there's the different aspects. There are some ops on scalability, and for which we have an issue later on. So I guess we can move to the next slide. 14. Basically, that is one open issue we have at the moment in the GitHub repo. Is the for the moment, basically, Vincent had a comment on partial reliability and saying that it impacts a lot the type of effects that you are using. So at the moment, we have just covered that by saying that partial reliability impacts the type of effects and the type of codecs that can be used, but I'm not sure to what extent we should provide more details for this point.
Okay, so maybe I can right now.
Yes.
Okay. So yes, it's pretty easy to address, I would say. Okay, so maybe I can answer right now. Can you? Okay.
I can hear you.
So yes, it's pretty easy to address, I would say. But let's do our best. There's some echo as well. Oh, can you do something? No. Okay, you can hear me at least. So quality is bad, but let's do our best. So yes, I think this issue is pretty easy to address. If you just mention that okay, for instance, we can have block versus sliding windows. It can impact block sliding windows. It can also be a matter of having small versus medium or large block sizes, or also the potential, the possibility to solve a subset of the linear system. So if you add this kind of
Thank you.
precision, I think it will solve this open issue.
So we have noted that down, and we will.
It's not a big deal, I would say, to address my comment.
So next slide.
You're welcome.
The next slide covers another issue that was more related to the appropriate parametric motivation techniques. You pointed out to C 81. So indeed, I think these points impact a lot on the flow that we are considering. Whether it is a constant bit rate and real time, or it is non-real time. That is what you have, at least in your in the appendix of that you showed us. So at the moment, we tried to say we just answer by saying that there's a general trade-off between the amount of redundancy to add depending on the transport layer and requirements. We do not go more into the details. I don't know if you think we should provide more detail, or you think this covers the issues, or more deep?
I would say for this issue, should be almost sufficient to add a reference already in RFC.
Okay.
I would say for this issue that it would be almost sufficient to add a reference to this already existing RFC. Once again, it's not that difficult, because the trade-offs are not only the amount of redundancy that could be added, it's more general than that. And we are back to the previous comment. For instance, you can achieve the same reliability, which is more or less what we try to achieve, while reducing the amount of redundant packets just by changing the nature of the flex scheme, or changing the block size if you are using a block size FEC scheme, things like that. So it's a bit more complex. But once again, I think that the IFC, the one I mentioned, 8681, addresses in some way that kind of topic.
So this is a comment from Jose on what is the current research going, and we agree with the quarter that we need to add some consequent text on that in the next version. That's really a missing point we have at the moment, and we need to work more on appropriate sections for that. We just list some and some refinement, but this needs to be more structured and more. We need to provide more things. So the next slide is on what we're going to do. So basically, there is a new version ongoing, and we plan to address the open issues as soon as possible. Also try to have some other research groups, because this affects the control. We see can attract some synergy with other working groups on this topic. So thank you very much, and I don't know if there are questions, because I'm using a strange. I cannot see the queue. If you have any questions, please.
Thank you, Nicolas. I think that in spite of the very bad audio quality, we managed to understand what you said. I think so, but it was quite difficult. Is there any question or comment from the audience?
I see Marcus in the queue, but I cannot.
We had many comments last time. It seems to be pretty calm this day. Marcus, can you speak?
You cannot speak. We cannot speak. Exchange on the by email.
Yeah. Okay.
Yes.
Marcus speaking. Can I raise some questions? Can you hear me?
Yes. Very well.
Sorry, I had some issues. So I'm one of the authors of the multipath DCCP draft and also of the multipath reordering draft. And I have two questions. My first question is, do you plan to have a reference implementation?
We have experiments with the FEC
you have already
under
one?
the transport. That is the one we have been using for the tests that we showed earlier. And it is more gathering different protocols. So it's not really specific to one protocol. So François had some, Michel had some implementations for FEC in Quick. So it depends on the protocols you are using, but we have in some cases running code.
Okay, because I could imagine that this would be a great opportunity to bring this to the multipath DCCP, and if you are interested in that, you are very much welcome here. My second question is related to the multipath reordering draft, and you already commented something on the mailing list. And after having a first read through your document, I could imagine that we can leverage some synergies, but maybe we have to take this to the mailing list. I think it would be easier on the list
because of the bad audio quality. But I think indeed there is opportunity for synergies here, because, and that's also why I sent the email saying that I guess there are some overlaps between the drafts at the moment.
Yeah, okay.
Thank you.
Yeah. Okay, very good. Yeah, then we will do it on the mailing list. Thanks.
You're welcome. Is there anything else? We have 1 minute. It seems it's not the case. So thank you, Nicolas. So we are waiting for the next version. Yes, there is some work to be done for this, for the comment that Marie-Jo made about the document. But otherwise, yes, the document seems to be progressing well. So once again, I'm confident that we managed to get something ready for not too far in the future. So thank you very much for the team, from you and the others, co-authors. Thank you, Nicolas. So now it's time to switch to the last session. The last presentation, sorry. Yep, from Morten.
Hello, everybody. Can you hear me?
Yes, we can hear you. We don't see you, but we can hear you.
Let me see if I can.
You have the floor.
Okay. So, hello, everybody. So I have a short presentation on basically a small comparison of latency and reliability for block and sliding window codes. So if you go to the next slide. So one of the sort of key reasons why we introduce FEC or ECC in a system is a sort of an effort, at least in a point-to-point case, to reduce or minimize latency. And if we look at what most transport protocols use today, which is ARQ or retransmissions shown in the figure on the left there, you can see basically that as packets are flowing through the network, if we have some packet loss, then we basically need to discover that at the receiver. We need to ask for retransmission, and that retransmission has to be delivered at the receiver again. And so basically, we're going to be paying in latency for the reliability with one RTT, one round trip time per retransmission. So this can be problematic for some applications, especially when the link latency or the network latency grows. Certain applications have latency requirements in the order of hundreds of milliseconds. And so if the link latency grows too large, then we don't have time for enough retransmissions, and we need to come up with a different solution for obtaining the reliability, but still meeting the latency requirements. So one of the things that is often suggested is using coding for that. And basically shown here in the diagram, right, the nice thing is that we can interleave these repair packets with our normal data packets. And once we sort of, if we experience some packet loss, we can use our repair packets to recover from that packet loss. And we can combine that with retransmissions, of course, but we can also run it sort of in a unidirectional way where we just have no feedback at all from the receivers. But there's still some latency involved here. Although this figure is basically seems like there's almost no latency in the recovery, that's actually not the case. And so one of the things that I want to share a little bit about today is the latency involved when using a coding approach. So if you take the next slide. So if we start by looking at something which is called block FEC or block ECC, basically what we are doing in those cases is that we are taking our data packets, we are putting them into blocks, and then from those blocks we are generating a repair. So in this figure here, I have two cases. In case number one, we have 4 blocks of 4 symbols. And in case number 2, we are gathering a larger block which contains 16 symbols. And so if we look at what the repair pattern looks like for those 2 different cases, if we look at the timeline that we have there at the bottom, you can see in case number 1, we are taking our 4 data packets and then generating 2 repair packets, then the next 4 data packets, 2 repair packets, and so forth, and the process continues. Whereas in case number 2, we are collecting the 16 data packets, and then we are generating the 8 repair packets. And if we look at the next slide, we can see that the worst case latency is the distance to repair, right? So the worst case that we can have is that we lose the first data packet, because then we have to wait the longest until we get any repair. The repair rate in both of these cases are the same, right? 33% of the traffic sent is actually repair data. But when we use the small blocks, we can minimize the distance to repair, and therefore also minimize the latency or the latency of decoding or repairing packet loss. And the graph there at the bottom basically just shows, with a 5 megabit stream and a 1280 byte packet size, that the block size really matters when you look at something like latency. There are certain codes that require very large blocks. And what you can see there in that figure is that if you have a block size of more than 500, you actually have accumulated 1 second of latency inside that block. Of course, this also depends on the source, how it's transmitting data, how bursty it is, and all these kind of things. But the block size can really have a big impact on the latency that we're going to observe. And for that reason, we typically want to make the block very small in latency sensitive applications. So on the next slide, we compared 2 different configurations, the case 1 and the case 2 that we had in the first in small with the video camera there. And you can see that on the figure on the left, we are comparing the residual packet loss. That is the loss that is sort of still that is unrecoverable, given a certain loss on the network. On the x-axis, we have the residual packet loss on the y-axis for the 2 different codes. And what you can see is that the larger block code, the one that sort of accumulates more symbols before it generates repair, is capable of handling a higher amount of packet loss before it actually sort of has to give up and expose packet loss to the application. Whereas the smaller block code is more fragile because it has less it has less protection against variance in the packet loss on the channel, basically. But the good thing about the small block code is that if you look then at the latency characteristics, you basically see that for the larger block, the larger Reed-Solomon code, you have the blue histogram there. You can see that the per packet delay that we're going to experience with that block code is actually sort of much more smeared out. And in the worst case, we have a sort of relatively high per packet delay, right? Whereas when we use the smaller block code, because we are generating the repair much quicker, we're actually able to cut the tail of that latency distribution by a lot, and we have most of our delay within a very sort of confined region, which is really what we want to have. So one of the things that sort of is interesting to try to investigate is how can we sort of bring these two things together, like get the residual packet loss performance of the big block code, but get the delay or the per packet delay profile of the small block code. And if you take the next slide. So one of the sort of ways that we can do that is by using the sliding window codes that have been also Vincent has done a lot of work on, and just to give you a little bit of insights on how those perform. So just to give you also like a quick overview of how they work, right? If a block code basically, as I said, what is shown on the right, or sorry, on the left. Where we're collecting 6 symbols, then we're generating 2 repair packets from those 6 symbols, and then in the next block we have the next 6 symbols, and then we generate 2 repair symbols for those packets. And sort of there's no overlap between the repair and the symbols. They're just, you know, one block is only protected by the repair symbols of that one block. If we look at something like a sliding window code, it works quite differently. But one of the key things that we can observe is that every symbol is actually protected by the same amount of repair. So if you look in the columns, you will see that every packet is included in 2 repair packets, which is exactly the same as with the block code. But what we're able to do with the sliding window code is that we're able to distribute the repair packets much more granularly inside the stream of the packets that are flowing through the network. And so if we look at the results for a sliding window implementation versus the Reed-Solomon implementation on the next slide, you can see that that actually using the sliding window where we have so to make it fair, we made the sliding window code only code over 24 symbols. So it's not keeping data inside the encoder for longer than the Reed-Solomon code does, but it's sort of sliding packets out of the encoder as they're becoming too old. And what you can see that, and then we have a repair pattern here, which is similar to the small Reed-Solomon code, where every 4 packets we generate 2 repair, and then we can see basically that previously the 6,4 Reed-Solomon code had a worse residual packet loss profile than the larger Reed-Solomon block code. But with the sliding window code, it's actually the opposite. Even with the more granular repairs, or the more sort of evenly spread out repair, we can actually handle more packet loss before we start to sort of expose packet loss to the application. And at the same time, we are able to get the same latency profile as we had with the small Reed-Solomon code. So you can see again the results from the larger Reed-Solomon code, where we have a latency per packet latency profile, which is basically spread out, and the worst case is pretty bad. So it means that sometimes, you know, packets experience quite a bit of latency, which causes jitter in the application and all sorts of unwanted effects. But with the sliding window code, we can actually narrow in and cut off that tail, because we're generating the repair needed to deal with losses much more often. So we can basically get sort of the best of the 2 worlds with sliding window codes. And so I think the final slide is just a quick conclusion on our side, right? So one of the things that you should really consider is that if you're using FEC, ECC, and you have a system where latency is a important parameter to optimize for, you should really consider sliding window codes over block codes. And really, when you look at the behavior of a sliding window code, you will see that sort of in the worst case, it will just perform as a block code, right? And if you want to read some more about sliding window coding, we have a lot of documentation on how they work and different ways to configure them on that link there in our own implementation called Rely. And if you want to ask me questions, either go to the list or you can also reach out directly at morten@steinwolf.com. And if you have some questions or feedback for it, I'll be happy to discuss.
Thank you so much, Martin. I have comments and questions, but is there anybody else?
There's me.
Okay, please.
Yeah, so I will sound like the usual broken record. Is there more research being done on this? I went through an NSF group on the future of broadband, and delay and bandwidth are not the only metrics anymore. So, so I would like to know the research, and also this seems to be, like, I would say it's nice you checked it, but I think we kind of knew that for quite a long time, right? Anybody like me who's done sliding anything in our career know that sliding will be better than block, because you can start decoding as the window arrives and not wait for the whole block. So I'm actually wondering what else is in that research?
Yeah, so that's a super good question. So there's actually a lot of interesting research to be done in this area still. So one of the things that we are looking at right now is that it's actually not true that sliding window is always better than a block. When the repair rate that you have for a sliding window code approaches the losses on the network, the fact that you have overlap in your repair actually means that you can end up in a situation where most of your repair becomes useless, because you're right at the boundary of where the sliding window code is able to you have a lot of dependency in the repair symbols in the sliding window code that you don't have in the block code, which is sort of, you get a block and then you get repair, and sometimes you're lucky that you get enough repair to deal with the packet loss, but the next block is independent. In the sliding window code, the repair that you currently get might be dependent on another block decode, a sort of a previous window decoding, and that actually can become a problem. So basically, one of the things that we're looking at right now, which is sort of open research, is how you shape the window depending on how close your repair rate is to the packet loss rate that you're observing. And so if you look, and the reason why that is important is that if you look at something like a video streaming application, you can't always increase the repair rate. It's not that you can just bring, like, then you run into congestion, right? There's some times where you have like a maximum amount of repair that you can put on top. And there actually, when you reach that ceiling, you need to start to manage your coding window. You can't just include as much as possible. You need to actually shrink it down, and so that you get more, basically you become like a block code. And then you can open it up again as your repair rate actually drops away from the packet loss rate that you're observing. So that's one open thing. Another thing which is currently being looked at is how you manage the coding window when you have heterogeneous links with different latencies. So basically, when you have like, again, you need to be able to control the coding window in time. And you need to be able to say, so you can imagine you have one link which has 100 milliseconds latency and another link which has 150 milliseconds latency. The packets that you're sending over the slower link, they can't include as many of the source symbols as the other link, because when they arrive, they are 50 milliseconds behind the other link. And that becomes important when you have an overall latency criteria that you're trying to meet. And so I think there's a lot of work that hasn't really been done, especially when we look at the more bringing it sort of closer to the applications. Last time I talked a little bit about content-aware coding, where basically you have to shape the window according to the video frames. So if you have like, if you have a coding window where you're just blindly saying every 4 packets I create 2 repair, that's not a good approach. If you have a video frame that's like 15 symbols, because you might have a case where some of parts of the symbol of your video frame is not getting repaired until the next video frame arrives, basically. And so you get like a sort of a latency penalty if you don't make your window adjust to the content. So you need basically your repair to follow the content that you are. So this is again very application specific, of course, but I think, you know, so that's some of the directions that we are looking at improving this, or working on the sliding window codes and sort of optimizing them. But I think that and I can mention also a fourth thing, which is basically there's been a lot of sort of work where you either split the solution into ARQ or FEC. So either you build a transport built just on ARQ, or you build a transport just built on FEC. There's very little actual transport protocols that try to combine the two, where you actually use ARQ when link latency is low, because then you have time to do ARQ. But when link latency grows, you need to basically switch out of that mode and start to use more the FEC to get some of the repair up front. Yeah, so that's some of the areas that we are working on.
And I think maybe you should mention that, should mention this in the future. And also, like, we're also looking at research communities here. So you said a lot of we, but is we just you, or is we many more universities? And I will give the floor to Watson after.
Watson last.
So Watson, please go.
This is really interesting. My question is the impact on the transport protocol of the loss? In other words, how close to the channel capacity is the good put of the channel on the ground?
So well, there's a bunch of trade-offs involved here, right? So if you use FEC underneath the transport protocol, you can effectively mask all packet loss, but it comes at a cost of increased bandwidth, right? So when you say good put, do you mean like what is the balance between the amount of repair that I'm putting on my network compared to the actual data that I'm putting in?
Yeah, I mean the actual data the application's transporting. Now, obviously, there's this issue with congestion control, but assuming that you've got a fixed amount of on-the-wire packets you can send, how close are you getting to your channel with a certain amount of loss?
Yeah, so I think looking at the graphs, you can see that the sliding window code is the one that gives you the best sort of reliability overhead trade-off, right? So having the same, in all of these cases, they are using 33% repair. So that means that 33% of the packets sent is repair, right? And there you're able to handle, I don't know what is the number here, like the sliding window code can handle 20% packet loss before it starts to sort of expose some packet loss to the application, right? Whereas the Reed-Solomon code is down to 10% or something, and then it starts to expose some packet loss. So clearly the coding that you can use that overhead more effectively with certain types of codes than others. But if you rely only on FEC, you have to have a certain amount of repair in order to deal with a given amount of packet loss on the network. And also how that packet loss is distributed is also has an impact.
Okay, I think we need to stop here. Thank you very much, Morten. Whatever you've said after, during the questions was extremely interesting, and I would be interested in having more detail on this, which is
Oh, I'm losing you, Vincent.
Involved. So yes, that's very important. So I hope that next time you will have time to share on this. We tried on our side a few years ago, but we've reached a situation that is not perfect. I was not totally satisfied with the way we initialize such parameters. So if you have more insight on this, that would be great. So we now need to switch, to close the session, the meeting. So thank you very much for all of you. I don't know, Marie-José, do you want to add something?
I was on mute, sorry. No, I think it was an interesting, I think it was a good meeting. I think it was very interesting. The work is very interesting. It shows that there's still some things that are moving on, and it's nice to hear. Thank you, everyone.
Thank you.
Thank you.
See you next time.
Bye.
Goodbye.